In this video, we're continuing our discussion of partial differential equations. In particular, we're going to talk about hyperbolic PDEs. So problems governed by hyperbolic PDEs have a finite physical information propagation speed. As a result, the solution at a given point P at time level n depends on the solution only within a finite domain of dependence in the simulation domain at times preceding time level n. And the solution at a given point P at time level n influences the solution only within a finite range of influence in the solution domain at times after level n. The physical information propagation speed, c, is equal to dx dt is finite. So two common hyperbolic PDEs are the convection equation and the wave equation. So with a hyperbolic PDE, we start with some initial condition, and we've got some boundary conditions defining the edges of our domain, and we march forward in time with this open boundary, and we have this finite domain of dependence and range of influence, and the information propagates at this finite speed c, plus or minus c. So let's look at the forward time-centered space method, FTCS method, that we introduced in the parabolic PDE section. So let's consider this for the convection equation with ft plus u of x is equal to 0. So recall this method uses a first-order approximation in time and a second-order approximation in space. So we get the expression shown here, and we can rearrange this where c is equal to u delta t by delta x. Is the convection number. And without going into the details, the stability analysis would reveal that this approximation is actually unconditionally unstable. So the FTCS is unsuitable for solving the convection equation and any other hyperbolic PDEs. So instead, let's consider the lax method. So the lax is a modification to the FTCS that gives a conditionally stable method. So this is the FTCS formulation. Now we can approximate this FIN as shown here, and then plug this into our formulation, and we get the expression shown here. So this is the lax method. The stability criterion for the lax method indicates that it is conditionally stable, where the stability condition is that c, which is u delta t by delta x, has to be less than or equal to 1. So let's look at an example considering the convection equation with the initial condition as shown here. So the initial condition is this kind of initial wave profile as shown here. And we want to solve this using the lax method for with different values of, or with one value of delta x. Delta x is 0.05, and then different values of delta t. So essentially, we're going to be using different values of c, our convection number. So the exact solution progresses as shown here, where the initial profile propagates over time. With t equals 0.05, we get this numerical solution using the lax method. And you can see that we get this this propagation over time, but this huge amount of dispersion and change in shape of our wave. It smears out as we progress forward. Here's the solution for c is 0.5, c is 0.9, and c is equal to 1. So when c equals 1, the numerical solution is actually identical to the exact solution for this particular case of the linear convection equation. This is not a general result. It's not true for nonlinear PDEs in particular. When c is 0.5, the amplitude of the solution is severely damped as the wave propagates, and the peak of the wave becomes rounded, as you can see as we progress in time. The general shape of the solution is somewhat maintained, but the leading and trailing edges of the wave tend to become very smeared out. And with c is equal to 0.1, the result as we progress in time after even 10 seconds, the numerical solution here does not even resemble the exact solution anymore. And it's completely smeared out. And you can see the amplitude is decreased by a large amount. So these effects are the result of numerical damping that is present in the lax method. So the presence of large amounts of numerical damping at small values of the convection number c is a serious problem with this method. So we can talk about this numerical diffusion and numerical dispersion. So the severe numerical damping present in the lax method is a result of the leading spatial truncation error in the difference equation. So recall that this was our approximation. So we can expand this out using a Taylor series as shown here. So let's plug this into our finite difference equation and we get the expression shown here, and we can cancel out the sum of the terms, as you can see. And we're left with this expression. We can then divide by delta t and recall that c is equal to u delta t by delta x. So we get this expression here, which is ft plus ufx is equal to all of this on the right-hand side. So this is the truncation error. So if you compare this with the original PDE, we had ft plus ufx is equal to 0. So this is all the leading truncation error. So as delta x and delta t go to 0, the first term on the right-hand side actually becomes indeterminate. So this means that the lax method is not a consistent approximation for the convection equation. If you recall what we when we defined consistency in the introduction section, as delta x and delta t go to 0, we need to recover the original PDE if the method is consistent. So this method is actually not a consistent approximation for the convection equation. Further, the severe damping present in the lax method is a result of this leading spatial truncation error term, which contains the second order spatial derivative fxx. So this term acts in the same manner as a real physical diffusion. And so the effect is called numerical diffusion or numerical damping. And you can see as our delta t decreases, which then drives our c down, this term actually increases. So then we get that more damping present. So for physical diffusion, the effect of the second spatial derivative is to diffuse or spread out the initial property distribution as time progresses. And the same result is obtained when the second spatial derivative is present in the truncation error term. So for the lax method, the numerical differentiation coefficient, delta x squared over 2 delta t, becomes very large as delta t decreases. So this effect is responsible for this severe damping present. And in more cases, in more general case, all even spatial derivatives in the truncation error contribute to the numerical diffusion. It can also be shown that all odd spatial derivatives in the truncation error contribute to numerical dispersion, which is a type of higher order convection which tends to distort the shape of the property distribution in space and causes wiggles in the solution. So numerical diffusion and or numerical dispersion are present in all numerical solutions of PDEs. So just to summarize the lax method, we determined that the lax approximation of the convection equation is explicit. It is a single-step method. It's inconsistent with the PDE. It is of order delta t in time and order delta x squared and plus order delta x squared over delta t. The accuracy of the solution increases as the convection number c is increased. For nonlinear PDEs, the exact solution is not obtained even for c equals 1. However, these results suggest that the most accurate solution might correspond to when c is equal to 1, and this is indeed the case. So the convection number c can be written as u delta t by delta x, which we can rearrange and call this delta t or delta x by delta t un, So C is equal to U over UN, where UN is the numerical information propagation speed, and U is the physical information propagation speed. So using values of C close to 1 causes the numerical information propagation speed to be close to the physical information propagation speed, which accounts for this increase in accuracy when C is close to 1. And this result is true for all explicit finite difference methods. From a characteristic analysis of the convection equation, it is known that information propagates along the characteristic paths specified by U, which is dx dt. And this information propagates from either the left or the right of the solution point, depending on whether U is greater than or less than 0. So this type of information propagation is referred to upwind propagation, since the information comes from the direction from which the convection velocity comes, which is the upwind direction. So finite difference methods that account for the direction of information propagation are called upwind methods. So let's consider the first order upwind method of the convection equation. So if the velocity is moving in this direction, or if U is moving in this direction, then we will consider our method, we'll take that into account in our method. So let's consider first order approximation for the first order forward difference of the time derivative, and a first order one-sided approximation in the upwind direction where U is greater than 0 for the space derivative. So this is our stencil, so you can see that instead of using a central difference, we're using a one-sided difference in the spatial derivative. And this results in this finite difference approximation here. So now we can rearrange and solve for Fi at n plus 1 and get the expression shown here, where again C is U delta T by delta X, which is called the convection number. So the first order upwind approximation of the convection equation is conditionally stable, where the stability criterion is that C has to be less than or equal to 1, again without going into the stability analysis. So let's look at the same example, considering the convection equation with the same initial condition as the previous example, and we want to solve this using the first order upwind method for delta x as 0.05 and various values of delta t to look at different convection numbers. So this is the result for the convection equation using C is equal to 0.1. And you can see that we get this propagation of the initial curve. It does have some smearing out and some change in amplitude and some rounding of the curve here. So comparing the exact solution shown in the blue and the orange for these two time steps, as well as all the kind of the dots showing the numerical solution. And this is the result for C is equal to 0.5. So you can see we're getting a bit better here, but we still have this kind of smearing out. And then for C is equal to 0.9. And for C is equal to 1, again, we achieve the exact result for this linear convection equation. So just to summarize the first order upwind method, we saw that it's an explicit method. It is a single step method. It is, if you look at the truncation errors, it is actually consistent. It's also conditionally stable, and it is convergent. However, we still see the significant amount of numerical diffusion in the solution. So let's look at a second order upwind method for the same convection equation. So here we are going to use a second order one-sided approximation in the upwind direction, and still a first order forward difference in the for the time derivative. So this approximation is order delta t plus order delta x squared. And if we go through this process, the resulting finite difference equation is actually unconditionally unstable, so it cannot be used to solve the unsteady convection equation or any hyperbolic PDE. Instead, if we use a method that is order delta t squared plus delta x squared, then we can achieve a stable method. So the finite difference equation in this case for the unsteady convection becomes the result shown here, where again C is equal to U delta T by delta X. And this is unconditionally stable with the stability criterion that C has to be less than 2. So this is a good method for solving hyperbolic PDEs. And it's also important to note that explicit upwind methods like this can be used in a straightforward manner they can be extended to solve nonlinear PDEs, systems of PDEs, as well as multidimensional problems. So let's again look at the same example, but here we're going to be using the second order upwind method for with this initial condition. So this is the result for C is equal to 0.1, and you can see that we get a pretty good solution where the wave that's propagating maintains the original shape relatively well. So again, this is the result for C is equal to 0.1, and the blue and the orange show the exact solution at those two different time points. And we can compare this with the first order upwind method for the same C. You can see that here we've stayed much closer to the original shape. Here we've got this much more numerical diffusion, and then we can compare this to the lax method where we have this huge amount of numerical diffusion. So again, this is the result with the second order upwind method for C is equal to 0.1. The amount of numerical diffusion is much less than with the first order upwind method. This is for C is equal to 0.5, C is equal to 0.9, and with C is equal to 1, we get the exact solution achieved. But again, this is only for this linear PDE and is not the case in general for nonlinear PDEs. So from this, we can see that upwind methods match the physics of hyperbolic PDEs more accurately than centered space methods do.